This is a random looking ink blot, but if I fold the paper, now that looks much more interesting. This blot has a mirror symmetry. It looks unchanged under reflection about a center line. So do our bodies. An object is symmetrical if there is something you can do to it that leaves it looking unchanged or invariant. This flower has a certain rotational invariance. Some invariances may seem trivial. The flower is also translationally invariant, but so is the shapeless stone. The stone is also time invariant, but not the flower. Symmetry or invariance makes a system more predictable. Emmy Noether took this idea to its logical end, proving that for every invariance there exists a conservation law and vice versa. The motion of a dropped object is the same whether we drop it today or tomorrow. The laws of physics, in this case gravity, are time invariant. This leads to the conservation of energy. Because if gravity changed with time, we could lift up an object when gravity was weaker and drop it when gravity was stronger, thereby creating energy. However, this object dropping is not translation invariant. The motion of the object is different whether I let it go from a lower elevation or a higher elevation. The symmetry is broken. But wait, if the Earth's object system is translated together in space, then this system is translation invariant. This leads to the conservation of linear momentum. While invariance and conservation are tightly bound together, there is a subtle difference between them. An invariance holds even when we change from one inertial reference frame to another, whereas a conserved quantity, such as energy, is a fixed value only within a reference frame, not across different frames. Special relativity tells us that neither distances in space nor separations in time are true invariants, only the separation in space-time. The space component of this invariant leads to the conservation of momentum, and the time component to the conservation of mass energy. Solving this energy equation for subatomic particles such as electrons led to the discovery of a profound symmetry. For every particle, there exists its mirror opposite, an antiparticle with the same mass as a particle but its opposite in other characteristics. A slight asymmetry in the first second after the Big Bang resulted in a billion plus one particles for every billion antiparticles. It is this little extra that now makes up all the atoms in the universe. A slight asymmetry has made our universe vastly more interesting by giving it atoms: Earth, life, you, and me.